Hello and welcome back to 5-Minute Chemistry. Today we are going to be talking about Avogadro's number, mole and molar mass because we can't stop talking about the mass of chemicals. So let's track back to the rule of constant composition, which told us that in a compound the elements that make up this compound have a fixed ratio, and based on Dalton's atomic theory we also know that this ratio is fixed as a small fraction if we are talking about the number of atoms in a compound. But the composition of a compound in mass is also fixed, but those ratios are a little more difficult to use. Those are not small fractions because the ratio of the masses of the different elements, or rather the masses of the atoms in those different elements, are going to be kind of random, and those ratios will not be numbers one can easily use. But when it comes to chemical reactions, atoms, they cannot be generated from nothing, and they also never disappear. If the atom is in your starting material, it has to end up in your products. So when we are designing chemical reactions, we have to keep in mind the number of atoms in each compound that we use. So the chemical reactions are much easier to be designed around the number of atoms or the ratio of atoms rather than the ratio of masses. But the problem is that actually when we are talking about any practical size of matter that we want to do chemical reactions with, the number of atoms will be huge. It's a very large number in any kind of sample that you work with in the laboratory. You have a lot of atoms. So if you have a sample of atoms, the mass of this sample will, of course, be the product of the mass of the atom and the number of atoms. And we already have some ways to describe the weight or the mass of atoms. We learned that every element is actually made up of different atoms, so different isotopes which have different masses. We cannot really just talk about the mass of a single atom. We prefer to talk about standard atomic weight, which is a weighted average of all the isotopes an element is made up of, basically a relative weight of atoms to the carbon-12 nuclide. So what we need instead is we want to have something that is more friendly to the SI units. So instead of just relative masses, we want to have real masses of samples, and the SI unit for mass is kilogram, but kilogram is a bit too big. So instead, this standard was built around the unit gram. And the question is that if I want to have a sample of atoms which has a mass in grams, which is the same number as the relative atomic weight of the atom, how many atoms do I need? Or you can rephrase this question based on the standard nuclide for the standard atomic weight, which is the carbon-12 nuclide. So how many carbon-12 atoms do I need to have exactly 12 gram of carbon-12 nuclides? Because the relative atomic weight is defined as 12 for carbon-12. So it turns out that for that we need around 6 times 10 to the 23. So it's 6 followed by 23 zeros. Well, it's a little more than that, 6.022, etc. And this is the number which we named Avogadro's number, or Avogadro's constant. But it was actually not discovered by Avogadro. It was named after him, but this is not his discovery. When it comes to the definition of units, the Avogadro number became defined as standard by the SI. So it is defined as an exact number, so it's 6.022140076 times 10 to the 23, and the unit of Avogadro number is mole to the power of -1 to 1 over mole, which means that if you have the number of atoms and divide it by this Avogadro's constant, because you divide by mole to the -1, the result you get will be in moles. So what does it mean? It means that if you have 6.022140076 times 10 to the 23 pieces of carbon atom, you have 1 mole of carbon atom. So you divide this number by Avogadro's number, or Avogadro's constant, and if you divide by 1 per mole, then you get mole. And Avogadro's number doesn't only work for atoms, it also works for molecules. So if you have 6.22, etc. times 10 to the 23 pieces of oxygen molecules, then you have 1 mole of oxygen molecules. But of course, because one oxygen molecule has 2 oxygen atoms in it, so if you have 1 mole of oxygen molecules, that means you have 2 moles of oxygen atoms. Now we come to the concept of molar mass. If we have 1 mole of carbon, so this is not carbon-12, it is carbon, the element, so it is composed of all the different nuclides. The weighted average atomic mass of these ends up being 12.01 for its standard atomic weight. And based on that, if we have 1 mole of carbon, we can suppose that it is made up of the same composition than what is used for the standard. So 1 mole of carbon will be 12.01 gram, or around 12.01 gram. So we can say that the molar mass of carbon is 12.01 gram per mole. So gram per mole is the unit of molar mass. So we define carbon-12 as having the standard atomic weight of 12, but what about its molar mass? So the new SI definition actually makes it non-exact, because kilogram is defined based on constants of the universe like speed of light and things like that, and the Avogadro number is just defined as an exact number. That means that actually the molar mass of carbon-12 is not going to be 12 by definition, because we have the Avogadro's number as a fixed defined number for 9 digits. So we know that it's at least until the 7th zero, it is 12.000 gram per mole. After that, it will not be definitionally 0. Okay, so this is it for today, and I will see you tomorrow.